when I start teaching limits, calculus, the first lesson of limits, I start doing some drawings, things like that. I start doing just this or something like this, or maybe something like this, or something like this, because it's important to understand limits by the idea of approximation. You cannot teach limit, which is a fundamental idea in calculus, without the geometrical perspective and without the analysis of the behavior of functions. I always tell my students, limit is approximation and limit is prediction of y values. I like this, predictions of y values. We are going to predict something. We are going to approximate something. And it's important to start looking at those beautiful drawings that we are going to be using along the content, along the lessons about limits. And then we move to a formal definition of limit. A formal definition of limit that the students can understand. Welcome to Math Topics. Welcome to the first lesson of this course, Calculus. I hope you like it. I know that when you think in any topic in calculus, many things come. Boom, 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 boom. We have limits. We have two sides limit. We have theorems. We have the squeeze theorems. We have the IVT theorems, the intermediate value theorems. So we have all of these things, and we're going to put that in a couple of lessons, maybe 2 lessons, maybe 3 lessons. But I want you to have a high quality course in front of you. Something that you can count. Something that you are going to follow in order to understand the fundamental ideas and the fundamental procedures. It's not only about formal definitions and formal structures, it's about techniques. How can we solve certain limits? And how can we do it fast? Again, welcome to Math Topics. If this is your first time, take a look in our channel and you will see a lot of math topics. Let's see now the first lesson about limit of functions. So now let's write the formal definition of limit. The limit exists if something like this happens. So what is the main player here? Functions. So what is the main player in calculus? Functions. So we're going to talk about function f of x. That's what we're going to do. We are not defining what type of function is this, just a function f. The limit notation is something like this. So when the limit of the function f from the right to x sub 0, let's say x sub 0 with the plus, the limit from the right is equal the limit of the function f when the x approaches to x sub 0 from the left, and those two limits are the same, then you can say that the limit exists. The limit when x approaches to x sub 0 of the function f of x is equal L. L is the limit. This is the formal definition, first thing that we do. So when the limit of the function f of x, when the x approaches to x sub 0 from the right is equal the limit of the function when the x approaches to x sub 0 from the left, those two limits are the same, equals L, then you can say that the limit of the function f exists when the x approaches to x sub 0 and is equal that value. That value is a y value. It's important to know that. The other thing that is important is that we are not worried about what's going on at f of x sub 0. We are not worried about that. We are worried about the neighbor of x sub 0. So you can draw the number line and you can tell the students we are not worried about what is happening at f of x sub 0, but we are worried about what happens to the right and to the left. What happened to those y values? What happened to those f of x values? And this is critical to the day that you teach limit, that idea. So this is the structure of the formal definition of limit. We are not talking about mathematical analysis. We are not talking about epsilon definition. So we're talking about the formal calculus definition of limit. When the limit from the left is equal to the limit from the right at when the x approaches at one particular point, exist is equal to L. And we can say that. We can conclude that the limit of f of x is L. When we do the formalization of this, the algebraic formalization of this, we can use now the graphing perspective. Let's see the graphing perspective. Now we are going to see this in action. We have a graph right there. You can see the graph right there. You can see the function f. Remember, what is the main actor here? Functions. And we have four possible choices, and they said the graph of the function y equal f of x is shown right here. Which of the following limit does not exist? So we are going now to practice the formal definition of limits. First choice. I want you to take a look on the first choice. The limit of the function f when the x is approaching to 0 from the right, we have to find the one that does not exist. So let me see what happens. So I have my pen right here, and I want to go over what they said here. Remember, the plus sign here means x approaching to 0 from the right. Remember, the formal definitions, if the limit of the function when the x approaches to x of 0 from the right is equal to the limit of the function f when the x is approaching to x of 0 from the left are the same, equal L, then you can say that the limit exists. So let's go over the critical x, which is 0. It's right here. And we can see we do not worry about what happened at f sub 0, because I know f sub 0 here is 2. No, f sub 0 here is undefined. We can see a hole right here. Can see a hole right here. So we don't worry about that. If the function is defined right there at x equals 0 or not, because we're not going to talk about continuous function, continuity. No, we're talking about limits in today's lesson, just limit. So we do not worry about what happened at f sub 0. Yes, it's a hole right there. The function is not defined, but this is another conversation that we're going to have in the next lessons, the lessons that are coming for this course. So we talk about the neighbor, your right side neighbor and your left side neighbor. Your right side neighbor in the approximation idea is over here. All the f of x values, they are very close to number 2 from the right. And from the left, they are very close to number 2. So because their two sides limits are the same and they are approximate to 2, we can say that the limit exists from the right and also exists from the left. But the choice A only asks for the right side. So from the right side, yes, the limit is equal to 2. No problem here. From the left, yes, exists from the left. But they only talk about when the x approaches to 0 from the right. Second choice, the other critical x values is 2. So I'm going to go over here. We are not worried about what happened to the function at f equals f of 2. We know that f of 2 is right here. But this is not the problem right now. The problem is what happened to the left, to number 2. So from the left, the function approaches to -1. From the left, the function approaches to -1. Clearly to -1. So let's see the next one. The other critical x value, 3. From the limits exist here. Here we have the full limit, right and left together. Okay, we say earlier today in a formal definition that when the two sides limits are the same, the limit exists at that particular x value. So from the left, when the function is approaching to 3 from the left, the limit is 1. And when the function approaches to x equals 3 from the right, the limit is 1. So the limit exists here because the two sides limits are the same. Final one. 2. We discover or we explore that when the x is approaching to 2 from the left, the limit is -1. We explore this before. Now we have number 2. So we need to check what happened from the right. So notice here that the function is going all the way to infinity here. All the way to infinity. When it's approaching from the left, f of x is going to infinity. It looks here that we have a vertical asymptote here. It looks like that. But this is not the point. We are not exploring vertical asymptotes yet. So it's approaching to x equal to, but the function is, boom, going all the way to infinity. So the left side limit is -1 and the right side limit is going to infinity. So because the two sides limits are not the same, we cannot say what we said earlier today, that the limit exists, L, when the two side limits are the same. So because this condition is not met, we can say that for x, when the x approaches to 2, from the right, the function is going to infinity, and from the left, the function is going to -1. So the two sides limits are not the same. The limit does not exist. And this is when you combine that integration between the formal definition, the notation, and the graphing perspective, is when you put everything together in your first lesson and the students understand what limit is about. What do you think? So let's do the final practice of lesson 1 to make sure that we understand the formal definition of limit and we understand how to do it algebraically, following the structure, and also using the integration of the graph, the graphing perspective. We have the function f on the right. You can see it. You can pause the video and you can try to do this. And then you can come back here and play and see if you did it right or not. Limit of the function f when x approaches to 3 from the left. So we go and find the critical point here with x equal 3, but from the left, the limit is 0. From the right, the limit is 0. So the limit when the function f approaches to x equal 3 exists and is equal to 0 because the two sides limits are equal L. Remember the formal definition. Now, curiosity, how much is the function when the x value is 3? How much is the y value when the x is 3? How much is the output when the x is 3? 0. We will see later in our next lessons what is the implication of this final thing. So let's do the next one. X approaching to 1 from the left. X approaching to 1 from the left, the limit is -1. From the right, the limit from the right, when the x approaches to 1 from the right, the limit is 4. The limit of the function when x approaches to 1 does not exist. Why? Because the two sides limits are not the same. F of 1 is defined here as 4. F of 1 is defined as 4. Final. Critical x value, 4. When the limit of the function f from the right to 4, from the left of 4, is how much? 1. So, when the x approaches to 4 from the left, the limit of the function is 1. From the right, when the x approaches to 4 from the right, the limit is also 1. So because the two sides limits are the same, the limit exists at x equals 4 and is equal to 1. And when you evaluate the function for 4, it's undefined because we have a hole. So we put here undefined. This is the first lesson of limit. I don't want to extend them more. I just want that you review the video. I just want that you see all the components, formal definition, right side limit, left side limit. If they are equals, the limit exists. It's not important what happens at x equals at x sub 0. When that condition is met, that the two side limit exist and they are the same, is when you can say that the limit exists. I don't want to repeat more this, but this is fundamental for what is coming. And remember, this choice here, we are going to revisit this choice soon. We're going to see what is the implication of this. I hope that you like the video. I love that you give us a like, that you support math topics, and that you spread the word. Thank you for watching. See you in the next lesson.